All right. So last time we stopped at the point where we want to design a good algorithm for finding the shortest time uh, for, say, car producers to decide which assembly line the car should be pushed through, right? So we have two assembly lines here, the entering point and then the exit point here. So we want to find out at any moment, for example, at this moment, uh, it takes 2 minutes to enter the station one of assembly line one, right? 4 minutes to go to station one of assembly line two, right? And then station one at assembly line one will take 7 minutes to finish the work, etc. And we want to find out what would be the shortest way to go from the entering point to the existing point, right? So last time we discussed a couple of things. Number one, can we use Dijkstra algorithm for finding what would be the shortest way, right? Uh, we will discuss about that a little bit later, right? Uh, After we talk about, say, the exhaustive search, divide concur, and then the dynamic programming algorithm, and we will go back to the point whether or not we can apply the Dijkstra algorithm. I said last time that yes, of course, we can do that, but let's see how it works, whether or not it's as good as the dynamic programming. Okay. So the exhaustive search, as we talked about last time, we take big O 2 power to the n, and that is not we can do, right? So nobody wants to have an algorithm that is exponential because if n is the number of stations, we may have 100 stations and 2 power to the 100 is way too much, right? So that said, the exhaustive search algorithm, even though it's correct, it works, but it has no real world application. Okay. So the second thing we did was, okay, can we just understand the problem and then try to design a recursive algorithm using divide and concur? All right. So last time we were working on the recursive solutions, right? The recursive solution based upon the observation that the fastest time to go from the entering point to the existing point is what we call the F star, right? And then the F star is the fastest way from the entering to the exit. It depends on whether or not we can find the shortest path to one of the stations of the assembly line one and two, right? So obviously, the shortest path to the exit point will be the shortest path of entering this last station plus the existing cost, comparing with the cost for reaching this point plus the existing point here, whatever smaller will be the smallest value we need for the existing point, right? So that said, we need to have a function Fij, right? So basically, Fij here will be a function or a method that will take into account two parameters, I and j, right? Okay, where I will go from 1 to 2 and j will go from 1 to n, where n is the number of stations, right? We assume that both assembly lines will have the same number of stations. All right, so that is what we have, right? So f star will be the mean of f1n plus x1 and F2n plus X2. Yeah. And then the base case is simple, right? The base case is that what is the minimum cost for reaching this station? That is 2 plus 7, or in general, the entering value plus the cost for finishing at the station 1, right? So that's set. For F1, 1 is easy. Same thing for F2, 1. All right, and then at any point or at any station, there are two possibilities. One is on the first assembly line. Okay? The minimum cost for reaching this point will be the smaller values of the minimum cost for reaching the previous station on the same assembly line, and the smallest value reaching the previous station on the other line plus the extra cost, right? So that said, we have the minimum cost here will be the mean of this or the mean of that, right? So that said, it will be F1 j minus 1 plus A1j, where j is the value at the current position, right? Okay. Or this one, right? So either this one or this one, whichever is smaller, all right? So that said, here we have F1j is the mean of reaching the previous station or reaching the previous station on the other assembly line plus the extra cost. And this one is for F1. Same thing for F2, right? F2j will be calculated in the same manner. Okay? All right. So that said, we have our function F1 and F2. So it's basically the method we need to write. Yeah. So we have to write down what is the function for Fij, right? So if I equal 1, then Fij will be here, E1 plus A11 if j is 1, the base case. Otherwise, take the mean, right? If j is greater than 2. And j here will go from 1 to n. Same thing, if I is 2, we have this. So basically, this one is the recursive function we have. Remember that this one is a recursive call. This one is a recursive call, right? Okay. So that said, we have the recursive solution for finding the Fij. And then the result would be, we have the F star, that is the mean of F1n plus X1 and F2n plus X2, right? That is what we designed before. Okay, so we have here the F star is the final thing we have to calculate, and F star is based upon our recursive function of Fij, right? Okay, so let's look at one example we have. If the assembly lines have 5 stations, right? Remember that we have station 1, 2, 3, 4, 5, and then we have the exit, and we have the entering. Okay, so now When we want to calculate the F star, we need to calculate the F15 and then F25, right? So because the F star here will be the mean of F1n plus X1, F2n plus X2, okay? So that said, we have to calculate F15 and F25 for this particular example. And let me choose a different color. And let's see, I remove the color here. And we choose a different color. Okay. So first we have to calculate F15. Following the recursive algorithm, right? F15 will be calculated based upon F14 and F24 plus the extra cost, right? Okay, so that said, in order to calculate this one, we have to call the function recursively for F14 and F24. Similarly, when we have the F25, we have to calculate F14, right, recursively, plus the extra cost for moving from the first assembly line to the second one. And we have to calculate this one again, right? So that said, each of these values will be calculated 2 times, right? So similarly, we will see that the values here will be calculated again and again 4 times. And this one will be calculated 8 times, right? So it's 2 power to the 1, 2 squared, 2 power to the third, and then 2 power to the fourth, right? So that said, the recursive algorithm here is simple, but as we already saw the pattern, right? Calculation will be invoked recursively again and again. And that said, it will take us how many times for this recursive algorithm if you have n station. So if we have n stations, what would be the complexity of this recursive algorithm? So this one will be calculated 1 time, okay, 2 times, 2 squared to the third, etc. So the last one, if you have n stations, right, you have 2 power to the n, okay? So the complexity will be at least 2 power to the n. Okay, so it looks like we have a recursive algorithm. It looks more serious than the exhaustive search, but it turns out that it's still exponential, right? So there's no difference between this and the previous exhaustive search in that we search for all possibilities, right? Okay, so the point here is if we choose, say, the recursive algorithm, some values will be recalculated again and again. It's because we go from right to left. Okay? What will happen if we try to calculate the values here, F1 1 first, F2 1, right? And keep them here. So in order to calculate the next value, F1 2, we don't have to call the function recursively, but simply use the value we already calculated, right? Okay. And then in that situation, we just have to calculate once, yeah? Once. So that said, finally, the values we have to calculate it here will be here 2 times, yeah, 2 plus 2, 2 plus 2 plus 2, right, etc. So if we calculate the values from right to left and reduce the value we already did before, the number of calculation will be how many value, how many steps, the complexity of the algorithm. If we calculate the values at each of the cells once from left to right, instead of from right to left using recursive calls. John, Juban, is 2 n's, right? Because here we have 1 to n, and then we have to do the same thing from 1 to n. So 2n in general is big O n. Very good. So that said, we have a better algorithm if we don't use the recursive algorithm, but we calculate the f values from left to right. Okay. All right. Now let's see what we can do with this example. All right. So here we have an example. Okay. We have the entering time and the exiting time. And at every station, we know how long does it take for finishing the work, right? And the cost for moving from one line to the other, right? Okay, so now instead of calculating the values, the f values from right to left, we will try to do it from left to right. Okay, so now first f1, 1, f1, 1. What is the value? What is the minimum step for going to the station 1 and finish the work there? What is the value we have f1, 1? Remember that is the base case, right? F1, 1 will be E1 plus A1, 1, right? That is 9, right? Okay, now F2, 1, what do we have? 4 plus 8 is 12, right? Okay, so now what is F12? F12 is here, right? What is the minimum cost to go from entering point to here? Remember that we have to compare between the previous one, right? So here we have F1, 1 is 9, right? 9 plus 9 here is 18. And then the other way is to go through the other assembly line. That is F21 is 12 plus 2. Okay. So the values at this cell, meaning the smallest time that we can reach from entering to this point, right? And finish the work at the station. So that said, it will be, right, from here, 9 plus 9, that is 18, right? And then from here is 12 plus 2 plus 9, right? Okay? So it's bigger than 18. So we have here 18. Now, besides the 18, which is the smallest time we can reach the station S12, we also want to record the direction, right? So that said, yeah, from here, right? If we want to reach this point, which way should we follow? Okay, whether or not we go through line 1 or line 2. Okay, if we go through line 1, it's 9 plus 9 is 18, right? If we go through line 2, it's 12 plus 2 plus 9, right? It's bigger, so we say that, okay, follow line number 1, right? So from here, we have line number 1. The F11, we have only one way, so we don't have to say what direction we have. Yeah, we don't have to say that because there's only one way. So we can neglect the values we have for the direction here. Okay, so that said, F12 we have 18. Now, similarly, we have F22. Okay, so what would be the value at F22? What do we have? Okay, fill in the values here for me. 11, okay, and then one more thing. What direction? Remember that we have the smallest value and the direction, whether or not we go through line 1 or line 2. Okay, so let's try it here. Okay, now F22, right? So we would need to look at, say, F11, right? F11 plus the cost here. F11 is 9, plus the cost is 2, and plus the values, I mean, the time we have to finish here is 5, right? The second way is to go with F21, right? F21, that is 4 is 12, we already have that, plus 5. Okay? So here we have the 12 plus with 5, right? Because going from this node to this node, or from two station, consecutive station on the same assembly line, costs nothing. Yeah, because they are next to each other, so don't need to spend time. Okay? So here you have 12 plus 5, right? It's 17. And it's through line 2, right? Okay, got it? So it should not be 16, right? Because here you need to have two different ways. One is from here. F21 is 12. 12 plus 0 plus 5 is 17. Or from here, F1 1 is 9 plus 2 plus 5 is 18, right? Okay, 9 plus 2 plus 5. Okay, so it's bigger than this one, right? So this one is 16. I think you are right. Okay, 16. So here we have 16 is smaller, right? So we have to pick the smaller value. Sorry about that. So we have 9, right? Plus 2 plus 5. 16, and we have, yeah, because I did not add them, so I missed the value. Okay, so here we have 16, and that is 1. Okay, so we have that 16, 1, right? It's coming from 1. All right, so probably we need to add them. Otherwise, when we look at this, we may think that this one is smaller. No, it's not, right? Okay. All right. Now we will fill out these cells, right? Okay. All right, so now we will fill out this value. Okay, this one means that it's at this point, right? So there are two possibilities. Then we would have F13 will be F12 is 18, right? Plus 3. 18 plus 3 is 21, right? Or here we have okay, 16 right? 16 plus the cos is 1 plus 3 is 20, right? So 20 is smaller, so we write it here, 20, okay? And that is from line 2, right? Because it's from line 2. Okay, so we have line 1 and line 2. Line 2 is smaller, so we write it down here too. Okay, we need to have the values for the lines here in order to construct the part. Okay? Without the part, we just know what would be the smallest value, but we need to know actually how we can go through the station. Yeah. All right. Now the next thing is here. What value we have for this? Okay, for this cell, okay, everybody try to write down the values we have here, 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 here. Okay, 5 cells. 1, 2, 3, 4, 5. So we go from left to right and top down, right? Or we can go from left to right, bottom up, same thing. Okay, so let's see what we have. I'll give you about, say, 5 minutes, and then you just type on the message what you have for this cell, right? This one is 23. Okay, so you can type in like, okay, F23, what is the smallest value and what is the line number. Okay, same thing here, same thing here, same thing here, same thing here. Okay, 5 minutes, everybody pull out a piece of paper and work for the numbers. Okay, anyone? First, F2, 3, what do you have? You have 22, okay? And what line 2, okay? And then F14, F14, 24, line 1, okay? And then F2, 4. All right, sounds good. And then finally, what do you have for the whole part? F star. F star means that you have the mean value of F15 plus 3 and F25 plus 6. Take the smallest one. 35. Very good. Okay. And what line? Because you have two options, right? Line 1 and line 2. So here you have 35 and line 1. Okay. Very good. So the results is here. Okay. So we have 20, 22, 24, 25, 32, 30, and then finally 35 is for the F star. Okay, all right, very good. So that is what we have as the dynamic programming algorithm, right? So the dynamic programming algorithm here is that we don't use the recursive algorithm, but we just have a loop, right? That will record the intermediate values from left to right. Okay, so it takes us just only big O n steps, right? So it's much better than the exhaustive search and the recursive algorithm that we have to calculate the values again and again, right? All right, so the algorithm is very simple, right? So we just have the base case for filling out the first two cells, and then for j from 2 to the n, we just compare the value of the previous cell, right? Add the extra cost, and then record the new values we have for every column, okay? For every column j. So that said, the algorithm we have here is big O n. Okay, so it's much better than the previous approaches. All right. Now, after we have the values we calculated, how can we build up the path? Remember that we just want to know not only the smallest times needed for finishing a car, right? So in this case, we have 35, right? And we know that we start with line 1. And hence, we just go backward, right? So we start with the values we have here, right? So we go to the next cells of line 1, right? And here we have line 1 again. So we go to the next cell of the same line, right? All right. So here we have line 2, meaning that we have to go to this cell, right? And then here we have line 1, so we have to go to this cell. So that said, we can bring out the sequence of stations as, okay, F11, okay, F22, or station 2 of line 2, right? And then station 3 of line 1, and then station 4 of line 1, and then station 5 of line 1. That's it, what we have, right? So we choose the values here for building up the path. So from here, go to line 2, go to line 1, go stay on line 1, and then go to the exit, right? So the algorithm for doing so is just by tracing back, right? Tracing back meaning that we just start from here, bring out line 1 of station 5, right? 1, right? Line 1, station 4, right? Okay, so from here, okay, line 1, station 3, and then line 2, station 2, right? And then line 1, station 1. So that is what we need. Okay. So it's very similar to matrix multiplication, right? We record the minimum cost and together with the breaking point. So here we record the assembly line. So it will help us to bring back the path needed to go from the entering point to the existing point. Okay, so very good. Just one to give you one hands-on exercise, and you do it by yourself at home, right? So here is another assembly line, and I change the value a little bit. Okay, so 5, 9, 2, 7, 4, 5, 3, and then etc. Yeah. Okay. You can just take a picture of this and then tell me what you have here. 5 star, and then also build back the path, the shortcut path. Right. So do it as a homework by yourself. Yeah. If you have any doubt, just send me an email and I can send you the solution. Okay. Now we have a dynamic programming that has the big ON's complexity, right? Now coming back to the question, can I use Dijkstra algorithm? Because it's very, very similar to finding the shortcut path on the graph, right? Okay, so can we use Dijkstra here for finding what is the shortcut path from enter to exit point? Yes, we can. However, we need to do something to prepare the graph. We cannot simply run the Dijkstra algorithm on this graph. Why? You have the graph here. If you run the Dijkstra algorithm on this, you have a wrong answer. Why? Yeah, I mean, you can specify the enter and the exit. Yeah, Dijkstra algorithm means that we find the shortest path from any node, like enter, to all other nodes, right? That's we don't need actually, right? We just need to know what is the shortest path from here to here only. Dijkstra will give us the shortest path from enter to every other node. It's a little bit more than what we ask for, right? But the key point is here. When you have a Dijkstra algorithm, right, you find the shortest path on the graph. Every edge on the graph will have a weight. But the biggest difference between this assembly line and the normal graph is that we have the time associated with each of the node. The time here. Yeah. And we have to count the time here as a part of the cost. If you run Dijkstra, it will simply take into account the weight here, the weight here, right? This one has 0, right? This one uh, this one has 0, right? So that's it. This graph is not 100% in the form of a normal graph for a Dijkstra algorithm, right? But we can easily change this graph to make it ready for Dijkstra. How? How can we change it? Did you see the point? On this graph, we have to count the number for this station, right? 9 is the time that this station would need to finish the work, right? It's not for the length of this edge, nor this edge. Okay. How can we change this graph into a graph that we can apply the Dijkstra? Yes, very good. We need to add the cost here to the next edge, right? Very good. So that said, instead of having 9 here, we have 9 here and then 11 here, right? So 9, 11. So same thing here. You have 4 and then 6 here, right? So after we do everything like that, then we can run the Dijkstra, okay? All right, so it's just a minor thing, right? But we have to go through every node and then check the adjacent, right? Update that, okay? Number one, if you have a graph, what would be the cost for us to go through every node here and update the value of the edge? Remember that when we have Dijkstra, we can choose an array, right? To keep track of the cost or the length of every axis, right? Okay, so let's say from 1 to 1, right? From S11 to enter, right? So we need to keep track of every distances here, right? Okay, so that's it. For every point here, we need to look for the adjacent nodes and then update the value of the edge, right? Okay, and now let's look at how the Dijkstra algorithm works. Okay, so here is what we have. I think it's about what page 31. Okay. Okay, so here is the Dijkstra algorithm. Okay, the algorithm, you can check it in any book, right? Okay, so uh, let me go through the algorithm with one example so we know how it works, right? Okay, so that said, we set the starting point. So here we have the nodes S, A, B, say C, D, right? And then we have the width of every axis, right? So first we have a queue of nodes that we have all of the nodes, right? And then we have the path at the beginning is empty. And now we just have a the distance, the shortest distance from S to itself is 0, okay? And from S to A, B, C, D, initialize with infinity, right? And then we just want to record what is the parent of A. At the beginning, it's null, right? Because we have not started the algorithm yet, right? Null, parent of C is null, parent of D is null, parent of B is null, right? Okay, so first, the Dijkstra algorithm will start with the smallest value, right, from S. So that's said from here you have what? 5. And the node, the next node is C, right? So that's said we will update this one. Let me change this one a little bit so it will not bother us anymore. One page. Okay, very good. So the next thing we have, hold on, this one, right? So C with the smallest value of 5, right? Okay, go to the next. Okay, now the next we have, it means that we have S is the starting point, right? And then we will try to update, okay? The shortest distance from S to C is 5, right? And then to A is 10 because we have only 2 axes. So we have shortest distance to A is 10, to C is 5. So we add 5 into the list of, say, nodes on the shortest path, right? So after we add 5 into here, we will try to update the value, right, by looking at the adjacency. Yeah. So that said, once we have the adjacency, right? Remember that the previous value of A is 10, but once we add 5, we have 5 plus 3, which is smaller than 10, right? So we update it 8. And similarly, we have 5 plus 2 is 7, 5 plus 9 is 14, right? So that said, it will go by looking at the adjacency nodes and then choose the smallest value, right? Okay, etc. Okay, so if we change the values of the axis for the assembly line like we did before, then we can apply this process, okay, Dijkstra algorithm. But what is the complexity if we apply the Dijkstra algorithm here? Remember that? Check the adjacency, right? Add the smallest node, I mean the node with the smallest distance, right? And then update the value. Okay? So what would be the complexity if we choose Dijkstra algorithm on the graph after we modify that? Did you still remember about the complexity for Dijkstra algorithm? All right, it's very simple. Okay, let's start with what we did before. We start from one thing, right? And then we initialize the values at every other node. And now we start looking at all of the adjacency nodes, right? So here we have two adjacency, and then go to update the values at every nodes, right? Pick the smallest one. Say from here, right? We pick the smallest one, right? We follow this path, right? Or let me backtrack to the previous example. This one. We already know that here is the shortcut path, right? But if we follow the Dijkstra, what will we have? Okay, we have the smallest one, right? And now we have to check all possible adjacent nodes, right? Okay, from here we have how many of them? If we apply the Dijkstra algorithm, we would need to have an adjacency matrix, right? So if you have n nodes, then how many values, what is the size of the matrix we have? N by n, right? So that said, you have at least n square values we have to check for the adjacency, right? And the same thing, okay, after we have it here, we have 2, right? And from here, what you have? 2 plus 7 is 9, right? Okay, 2 plus 7, and 2 plus 7, okay, plus 2, right? Plus 5, right? So from here you have 2 plus 7 plus 9 to this point. Now you have 2 plus 7 plus 2 plus 5. Okay, this one you have 2, 7 here, and 2 plus 5, 7. So this one will be the smallest way, right? So you would have the same result. However, the cause is that from here, we need to check all of the adjacency nodes. To pick the smallest one from here, choose the smallest one from all possible adjacency, right? And in the Dijkstra algorithm, you need to have all of the adjacency values on the matrix that has a big O(n) square. Okay? And that said, the Dijkstra algorithm will have big O(n) square. That is one version of is the traditional Dijkstra algorithm. The fastest Dijkstra algorithm is based upon what we call the heap, the min heap. You already learned about min heap, right? So in that situation, we choose linked list and we choose min heap. So we don't need to have this, okay? But for the min heap, what would be the cost for sorting the values on the heap? You already learned the sorting algorithm if we choose heaps, right? It's called heap sort. What would be the cost for heap sort? Big O(n) log n, very good, right? So that said, if we used the Dijkstra algorithm, the best thing we can do is big O(n) log n. However, before you can run the Dijkstra algorithm, you need to change the value of every node here by adding that value to the edges, right? So in that situation, it causes, if we use matrix, it causes n square step, okay? And if we use linked list, it may take, say, big O n. However, the Dijkstra, the best thing we have is big O and log n. So in other words, yeah, Dijkstra algorithm can be used, provided that we change the matrix, we change the graph, okay? As we already talked about, right? We change the graph, apply the Dijkstra, but the Dijkstra is still slower than the dynamic programming we have, right? Okay, but having the Dijkstra algorithm is something, worth to look at. And we found out that, yeah, it takes big O n square if we use matrix, and it takes n log n if we use min heaps, right? Okay, so that is about the, say, assembly line. And don't forget to do the homework exercise here by yourself, okay? All right, so you can see that the matrix multiplication, and multiplication of sequence of matrices, and the optimal assembly line problems, they have something in common. That is what we call how to solve the optimal problem using, say, dynamic programming. In other words, instead of recursively call the function again and again, we try to remember the values of smaller problems and then build up the solution for the bigger problems based upon the memorized value we did before, right? So that said, the problem is for finding an optimal solution, right? And we have, say, the bottom-up manner, okay, not the top-down. Okay? If we have the top-down, then we have to use a recursive algorithm, right? And as I mentioned before, recursive algorithm tends, usually have to recalculate the values of some smaller problems multiple times, actually exponential number of times, right? Okay, that is what we have for, say, how to use dynamic programming. Okay, any question you have about, say, matrix multiplication or the assembly line? No question, right? So you should be able to, understand the algorithms, right? And the homework assignment is simply understanding the algorithm I went through in the class, implement that. You can use any programming language you like, right? But Java is the most, important programming language for businesses. So that's why I would encourage you to use Java if it's possible. Python is okay. C, C++, they're okay. Okay, you can use any of the programming languages we have on the world. I can accept them all. Okay. So the next problem I will introduce a little bit today is about the longest common subsequence. Why I choose this problem this time? Uh, I did not go through this problem when I taught algorithms last year. The reason for this is that this algorithm has many applications for, say, computational biology. And remember that we have the pandemic, right? The COVID-19 pandemic. And then one of the work for the vaccine developers is that to identify the common part of different versions of the viruses. So, for example, we want to know what is the difference between Omicron and the other strains of the COVID viruses, right? So we want to know whether or not they have something in common. So that's why we want to use what we call the longest common subsequence, right? So you have two different versions of the viruses. You know that, I mean, all of the DNA we have is based upon ATCG, right? The nucleotide, right? So any combination of ATCGs will build up the different genes, right? And then different protein as well, right? So we want to know between these two sequences of nucleotides, what is the longest common thing? And you know that in two genes, there's some insertion, right? When the virus mutated, there may be some insertion into the genes. So, for example, the original gene is here, and some nucleotide may be inserted, and at the same time, some may be removed, right? Or deletion from the original gene. So the main thing is that if you have two different versions of the virus, we want to know what are the common parts of them, right? So once we can identify the common parts, then we can design the vaccine that can capture that common part, attack that common part, right? And it will be more helpful for the vaccine to attack both of them. Okay? If we just simply focus on say virus version 1, and it has nothing in common with virus version 2, then that vaccine may not work for the second version of the virus, right? So that's why I want to pick this problem. Okay? So it's very common for computational biology. Okay, for example, here, I mean, for the genes, we have ATCG as the letters, but in general, we can have any alphabet. Okay, for example, we have a sequence here, A, B, C, B, D, A, B, and then the next sequence can be anything, and we want to know what would be the longest common subsequence, right? So if you have a sequence here, a subsequent of this one can be any list of letters from here. You go from left to right, you can pick A, and then C, B, and then A. So A, C, B, A is a subsequence of X. Right? You just have to have the letter from left to right. You can skip some, right? And you can use some, and it will be a subsequence. So for example, here we can have A, C, B, A, or you can have A, B, D, right? If you choose A, B, B is a subsequence, right? Or B, C, D, B, okay? B, C, D, B is another subsequence, okay? So we have two sequences here, X and Y. Okay. We want to know what would be the longest subsequence. For example, in this case, you have X and Y here. You can have B, C, B, A from the first B, C, B, A. Okay, we take three of this and one of this, right? You also have B, C, B, A here, right? And this subsequence has 4 letters. And later on, we will show that is the longest subsequence because there's nothing longer than 4 for both of the sequences here, right? And the longest common subsequence may not be unique. Okay? We may have more than one solution, right? And that said, here, the problem is given 2 sequences of letters, find all longest subsequence or longest subsequences of them. Okay, we want to find not only one, but all of the longest subsequence if it's possible. Another example is that using the same sequences, right? Here, if we pick B and then DAB, is also a longest subsequence because here you also have B, D, A, B, right? And this one has 4 letters. It's the same like this one, 4 letters, right? So here we have 2 longest subsequences of X and Y. All right. All right, so it's the problem we have to solve maybe next time, right? And again, we will go through the process that first, how can we solve this problem? Any algorithm. So we usually start with the exhaustive search, right? And then analyze the complexity. And then after that, we will design a divide and conquer. And then analyze that divide and conquer using recursive algorithms. To see if it's a good algorithm. And then finally, we will try to have a better one by using dynamic programming, meaning try to calculate the values for the small problem first, and then remember the result and use the memorized results in order to build up the solution for the bigger problems. Okay? All right, so it's some motivation for you for the longest subsequence problems. Yeah. Any question you have? Okay, if no question, then I will stop here. And don't forget to start working for your assignment. Okay.